Hello everyone, and welcome to the course of Nanobiophotonix, touching our daily lives. This course, this is the week one discussion, and I am Udiptya. I am from IIT Madras, currently doing my PhD here, and I work on fiber optic, developing fiber optic. Um, uh, Basically, I work on diagnostics, which are based on optical fiber sensors. And this course is also kind of quite related to whatever I work on. That makes it interesting for me to also teach or help you with the through the course contents. Yeah. This is the week one, so we'll go mostly through the basics of it. So basically, what is nanobiophotonix? Why we need to study nanobiophotonix? Why do this, and why photonics and why biology also is something that we will touch upon. Additionally, we will have some problem solving questions. So it's the structure will be such that we'll have kind of a weekly summary, and so it's kind of weekly summary, and then follow up with some problem solving questions. And then you can also so I will try to collate some questions which are similar to the assignment questions, and that will essentially help you with solving the essential assignment questions, and also help you to visualize the research, and finally you can use it for your you will get an idea on how you will face the questions in the final exam. Yeah. I will try to make it quite similar to the assignment question, so that it is a little bit relevant to you. Also, the questions may not be always in a multiple choice fashion, so I'll try to do that so that you get a complete idea of the subject too. Yeah. Feel free to stop me if you have some doubts, and yeah, it should be. It's better that it is interactive. Coming to nano biophotonics, uh, it's good to address the title first. So it's kind of made up of photonics, yeah, photonics, which is study of photons, yeah, not study of light, study of photons, yeah. And then you have nanotechnology, so nanotech, which is study of materials which are from 1 to 100 nanometer. One of the edges of that particle should be in the range of 1 to 100 nanometer. Yeah. And then you have biology or biotechnology. Maybe if you talk about more engineering, it will be biotechnology. Yeah. So now as you have seen, people have studied on separately on photonics, separately on nanotech, and also biology, biotechnology is also a subject in itself. People do their masters, their PhD on one of these topics also. Yeah. But then now people have started to interact the cross domains, yeah, using photonics in biology, or finding biological applications, some things in for through photonics. So that study that is called as biophotonics. Yeah, biophotonics. Also, you can have nanotech and biology, a lot of applications coming, which is nano biotech. Yeah, nano biotechnology or nanotechnology also there. And then you have nanophotonics also. Yeah, so very intensive applications and physics kind of thing. And then when all of this now are interacting together to make this what we are studying as nanobiophotonix. Yeah. So so why it is important? Yeah. So why it is important is this nanobiophotonix have very important role in two very important sectors. Yeah. One is diagnostics. Yeah. So you have seen how diagnostics are very important during the COVID days. uh, yeah, lot of it depended on vaccines and also on the RT-PCR tests and also uh, apart from the public health, the economy also, kind of a full system in the public society depends on a lot on diagnostics. Also, you can see that when we had COVID, a lot of the other diseases that were there present also got neglected. So you also need some alternative diagnostic platforms also to be developed, such that when such kind of pandemic comes, the focus on the other diseases also doesn't get diverted. Yeah. So this is an important thing to consider. So in diagnostics, you can have two things. One is molecular bioimaging. Yeah. So imaging of cells, yeah, a very important application area for those who are working in biotechnology, yeah, or cellular imaging. And then you have biosensing. Yeah. So, can anyone tell whether we do see some nano applications in biosensing, in something that you might have seen in the daily or like normal use? Can anyone point out? So we do have something called as LFA, lateral flow assays. Yeah. So lateral flow assays, maybe pregnancy strips. Yeah, you have seen pregnancy strips, or and also the rapid antigen tests for COVID will have this kind of LFAs. So LFAs essentially are some kind of plastic covering in which you have two lines here, test and control. So here, if someone is pregnant, they essentially put the sample here, yeah, and then the sample will go ahead. If the patient is pregnant, if the like the user is pregnant, then the test and control will turn as pink, yeah. And if it is a non-pregnant sample, then it will be single pink, yeah. Only one will turn, only the control will turn. This pink essentially is not a dye, it's actually gold nanoparticles. So you see how nanotechnology has applications directly at and biosensing, yeah. That is quite commercial. You will have a lot of examples in the research field. Then what you have is in therapeutics too. Yeah. Therapeutics is an important umbrella. So therapeutics also you have a lot of applications. So you have light based therapies. Yeah. So what you will do is you will put some nanomaterials, and those will be targeted to one cell, one particular cancer cell or something like that. Yeah. And then you can essentially uh, incident it with some light, maybe IR light or something like that. That will essentially start to generate heat, yeah, and then you can so because of that heat, yeah, the drugs will get porrated to the cell. So such kind of light based therapies are also possible. And then you have nanomedicine, yeah. So nanomedicine nowadays, people want targeted drug delivery, yeah. So whatever they will put some receptors on these nanoparticles, and these nanoparticles will carry the drugs too, and you can directly target the cell of your interest. So rather than going here and there, the drug can directly be targeted. Mostly what you do is we in terms of cancers and such, we usually have a chemos, yeah, and they start to have effects in the other parts of the cells too. But if you have a system which can have a targeted approach, so the lot of the side effects can be minimized. So yeah, so nanomedicine in that terms, it will help in targeted approach and also on effective delivery. Essentially, you will only need lesser amounts of drug to generate the similar effective response. Also, when you have medicine, it can get eliminated from the body quite fast because of the urine, through urine or such things. So such that this it is nano, it can be quite travel quite fast to the target, and then can it stay there for a long amount of time. So that, and also some aspects of therapeutics that nanomedicine helps. Okay. So why we do this? So a lot of things we have discussed, but I want to point it out again. So first is it's light, being light, use of light. It's quite non-invasive. Yeah, you can control it through outside, or maybe some, in some applications, maybe minimally invasive. Yeah, to the cells. Yeah. Then it is also non-destructive. Yeah. So maybe using visible range, it's usually uh, uh, non-destructive to the biological cells. And it can be used for fundamental applications. So really seeing what happens in the cell, in a single cell or like group of cells, to maybe making a device. For example, the LFA that I told you, it's a kind of a device. Yeah. So you have lot more complex devices, but essentially this field spans from understanding fundamental understanding of a cell to having something that is quite application oriented in terms of sensing and nanomedicine. So you will have devices to fundamental studies also coming up. So benefits is it is quite fast. Yeah. So the nowadays you have very fast detectors, yeah, which can detect this changes in the photons quite faster. Yeah. And also the LEDs that makes it quite they are basically very good sources of stable light. Yeah. And also in quite cheaper rates, cost. So you don't need nowadays lasers. You can have quite LEDs which can also serve a lot of applications. Obviously there are some applications in which laser is a must. So as it said, it has become more sensitive. Yeah. And with minimal error, because of the very good photodetectors or photodiode systems that are there. And it is very much potent, very much less affected by the external factors like temperature, pressure, and things like that. So why photonics? Why study of photonics is important is because we usually have the visible range of light. Yeah. So we have this visible light. Yeah, which starts from maybe 400 nanometer and spans to maybe to 700 or 800 nanometer. Yeah, this is the light we can essentially see. And uh, with this kind of nanoparticles or this contrast agents which absorb light at, so things we can't see, basically things which are maybe less than the visible range, like the optical microscope. What we do is usually have some kind of nano tools which makes it easy to see those things too. So actually this nano as a tool helps us to stretch beyond the visible range, but using the visible light itself. So that makes it like as we had told, so if you are using UV, it can actually damage the cells here. So UV, as you've seen, it can UV light can essentially cross-link the DNA itself. So always doing like high exposure or long duration of UV can be destructive to the cells. But if you have a visible light, it makes it you can essentially use it for your applications. Yeah. So coming to why biology is an important topic essentially because it has a lot of social relevance. Yeah. So starting from biosensing, uh, so it has a high social relevance. Yeah. So you have all the understanding of a lot of application oriented this nowadays biology have become. So you have diseases, burden of diseases, for example the COVID that has happened. Yeah, diseases. Then you have problems like AMR, cancers. Yeah. Yeah. So you have pandemics. Yeah, COVID was one such. You have diseases like TB which are already there. Yeah. So a lot of other applications also will be there. So which makes it so there are some areas that can be addressed. For example, first is imaging. Yeah, using contrast agents, nano contrast agents. Then you have a point of care sensing. So a lot of nowadays the sensing is based on centralized facilities. So basically in all villages or all tier 2 cities maybe they won't have a biosensing setup. So what they will do is they will pull up the collect basically the samples and then send it to the centralized laboratory from where they can do the sensing and give the results. So that makes a long delay, yeah, in providing the results. So it is good to democratize these technologies so that everyone can have the same similar kind of access to the healthcare. Yeah. Then you have problems on theranostics and yeah, maybe molecular level imaging is also another study. Maybe it will come in imaging itself. Molecular level understanding of. Yeah. Yeah. So, any doubts till now?
Can I ask some?
Yeah, sure.
Yeah, you in your previous slide you said that photon and light. So
Mm.
you said that you can detect, you use photon to detect our emission, and also says that you use light. Those are highly visible light. Those kind of things that we can detect and see the image. Can you quickly explain what these things?
Can you ask me again? Like, can you frame it again? What is the
Yes.
actual?
So use in your previous slide you says that photon, you use photon to
Yeah.
detect sorry, to use photon, then we excite with this photon exciting subject, and then we capture with the detector, then we can do whatever action we can do. Then you also tell that we use high imaging light or some kind of things. So can you explain about this photon versus light?
Yeah, yeah,
I
yeah.
don't know.
Sure. Understood. Understood.
Okay.
So you basically, so what happens is, so so usually when you have a optical microscope, yeah, or maybe things like so, as the example was the LFA, yeah. So lateral flow as I told. So there you will have antibodies in which so it basically it has the antigen here, okay, and then you have antibody, okay, understood. So this complex, so barely this is how much, maybe 15 nanometer. Yeah, this will be 15 nanometer and this will also be 15 nanometer maybe. But and on this you have a gold nanoparticle which may be 50 nanometer. So everything close maybe adds up to 100 nanometer. Yeah, it is not possible for our eye to see this, but this nano marker or this nanoparticle makes it visible, for makes it us makes it perceivable for human eyes, and that makes it applications. Yeah. So you will have this is one of the example of using nanoparticles as contrast. You will have some field called a dark field imaging. Yeah, which uses visible range light, and then also you can have you can go down the resolution mark. So usually what happens is Yeah, that's the thing that I wanted to let you know, that nano makes it a lot easier to operate in visible range. Maybe maybe in some cases you had to go down to this down the wavelength chart, maybe go down to the UV, but that is may not be very much suitable for biological applications.
So basically, I use confocal microscope. So I operate a confocal microscope.
Yeah.
I use. So that's why I ask. I want to know that. So basically, we use a filter
Fluorescent.
light to see our yes,
Yeah.
we use filter light to what you call view our subject under the microscope. But when we use confocal or fluorescence laser, then we see something else. But
True.
yes, so that's why I want to know that can we do our imaging with this normal light things like filter lights, like blue light, a
Yeah,
green light,
fluorescent
and
is another method of the contrast enhancement. Yeah, it is just another technique to enhance the contrast. So you will
okay.
have some other types of like nano based uh, fluorescent also. So that is also another things. So you have something called as metal enhanced fluorescence. Yeah. So actually, if you have a fluorescent marker in nearby a metal, maybe metal in case of AU, gold nanoparticle. So the amount of fluorescence essentially increases, and this is very much dependent on the distance. So that is called as MEF, metal enhanced fluorescence. So yeah, things like that. So maybe what you are doing in fluorescence, that is another technique. Like it's a technique which may not have nano aspects in it, more of optics involved as such in the terms of the microscopic filter in terms of fluorescence cubes, yeah, and the optical objectives. But then there are techniques which incorporate nano, and then it can have other applications too. So usually what you have is you might have heard about something called as Abbe's diffraction limit, yeah, which tells that you can only go down lambda by 2, yeah, something called as
Yes.
Abbe's diffraction limit, yeah, maybe like that. So essentially with 400, or maybe you want, what you see is 500 nanometer light, what you can essentially differentiate is it's something that maybe in the 250 nanometer, yeah. So that is the diffraction limit that you can essentially see. Anyway, we'll actually go on detail in this. So that time we'll see how the diffraction limits or something like that. But just to give you a primer, that's the use of photonics. Fluorescence is another example. But how you can club it with nano and make it something else, like maybe enhance its application. That's what. Is it okay?
Yeah, yeah, you can continue.
Yeah. So yeah, let's just question. So maybe we'll have some 5 minutes for each question, and then we'll discuss it.
So how I can use this nano thing with my fluorescence microscope or multiphoton microscope?
That is something like you have to see in detail, but
Okay.
yeah, maybe that you might have to just, these are just this is the less, like this is a course through which you will know about this field, and then you have to in specific things you have to maybe yeah, that you might even think through it.
Okay. Okay.
Okay, the answer here is all of the above. So, as we had discussed, nanobiophotonics is a field that combines nanotechnology, biophotonics to explore and utilize the interactions of light with biological systems at the nanoscale. Yeah. So, it offers wide range of applications in various areas of biology and medicine. So, the following is an example of biophotonics based medical diagnostic technique. So the answer is OCT. So optical coherence tomography. It is an example of biophotonic based medical diagnostic technique. OCT is a non-invasive imaging technique that uses light waves to capture high resolution cross-sectional images of biological tissues. So it is commonly used in ophthalmology to examine retina and anterior segment of the eye. And it has other applications in other medical fields such as cardiology and dermatology too. Yeah. So what is the fluorescence microscopy used for in biophotonics? Yeah. So yeah, imaging of live cells. But I do believe that there are now specific fluorophores you can essentially design, which can also may be useful for temperature monitoring or quantifying the concentration of biomolecules. So you can actually develop um, uh, some biomolecules or molecular beacons or something like that. You can essentially quantify the concentration of biomolecules too. So yeah, maybe imaging of live cells and tissues is one of the important uh, thing, but other things also is quite possible. Yeah. Which of the following is not a potential application of biophotonics? So, yeah, obvious kind of answer. So, cancer diagnosis and treatment, neuroscience research, and environmental monitoring are applications to biophotonics. Which type of light source is commonly used in biophotonic applications? So the answer is visible light. So visible light is the type of light source that is commonly used in biophotonic applications. So biophotonics focuses on interaction of light with biological systems, and visible light falls within the range of wavelengths, which is 400 to 700, that can penetrate biological tissues and cells effectively. Visible light is safe for imaging and therapeutic purposes, making it an ideal choice in various biophotonics such as fluorescence imaging, confocal photodynamic therapy for cancer treatment. So this is a question in which green light of wavelength 500 nanometer carries an energy of what? So we know that, yeah, E equal to hc by lambda, yeah. So what is h? It's the Planck's constant, yeah, 6.626 into 10 to the power minus 34 into speed of light is 3 into 10 to the power 8, yeah. And lambda you have to put 500 nanometer as given in the question. So nanometer is 500 10 to the power minus 9 meter, yeah. So what we get is, if we calculate this, how much you will get? Let me calculate. Okay, this is coming around 3.98 into 10 to the power minus 19 joule. Yeah, this is the energy there. Okay, so okay, it's in joule, so we want it in electron volt. Yeah, so 1 electron volt is 1.602 into 10 to the power minus 19 joule. Yeah, so E equal to 3.98 into 10 to the power minus 19 joule divided by 1.602 into 10 to the power minus 19 joule.
2.4843.
2 point
4843.
okay, yeah. So yeah, so we will put
Option B.
option B, yeah. So B is the correct answer. Okay. Yeah. What is the role of photodetector in biophotonics? Yeah. Okay.
Sir, is this option B, sir?
Yeah, just write it down. We'll wait for 5 minutes so that like it is anyway getting recorded. So uh, yeah, we'll discuss it after 5 minutes. Yeah, the answer is B. So it measures intensity of light. So in a photodetector is an essential component used to measure the intensity of light. So when light interacts with the biological samples of tissues, it produces signals that can contain valuable information about the sample's characteristics or behavior. So these photodetectors are designed to detect and convert these optical signals into electrical signals, which can be further processed and analyzed. Yeah. What is the purpose of optical coherence tomography in biophotonics? So the answer is to image the internal structures of biological tissues with high resolution. Yeah. So OCT is a non-invasive imaging technique that uses light to obtain high-resolution cross-sectional images of biological tissues, and as we had discussed, it is commonly used in ophthalmology and other medical fields for imaging structures such as retina and blood vessels. So this is a exercise question. So consider a photodiode that has a band gap energy of 1.43 electron volt at 300 Kelvin. What is the cutoff wavelength of this device? Did anyone solve it?
Sir, I'm still solving it.
Okay. Maybe we'll wait 2 minutes then.
So the options,
Options not there. Are you done?
I'm getting around 900, sir.
Actually, I also don't know. Look, I also have to solve it. So okay, we can solve it. Yeah. Yeah. So yeah, we'll start with E equal to hc by lambda. Yeah, that's the equation, and we have
H is equal to 6 point.
yeah. So first we have to convert the energy. Yeah. So energy is what we have is 1.43 electron volt into 1.609.
609 into 10 power minus 20.
Yeah. So this will come as what is the value?
1 second, sir. 2.2908 into 10 power minus 20.
Minus 19.
Yes, sir. That, yes.
Okay, okay. So and we have, so we can put it in the yeah, equation 1. So 626 into minus 34 into 3 into 10 to the power 8, and lambda we have to find out. Okay. Okay, so when we do it, we have lambda equal to
868 nanometers. Okay.
10 to the power minus 34 into 10 to the power 8 and 2.29 minus 9. Yeah, correct. Yeah.
Yes, sir.
So what we are getting is
868 nanometers.
so okay, 868 into 10 to the power minus 9. Yeah, or 868 nanometer. Okay. Yeah, that's what I have to solve it. Yeah. Okay. Okay. Next question. I believe this is the last one. Okay. A point source of light is 12 centimeter below the surface of a large body of water. So what is the radius of the largest circle on the water surface through which the light can emerge from the water into air? Yeah. Okay.
So no options for this, sir.
No. Like normal solving only. So I also don't know the answer. I have to solve and find out. Solved.
Yes, sir.
So how are you solving it?
So, sir, the first step is to find the critical angle.
Okay.
By air by water, that is 1 divided by 1.3 is around 0.75.
Mm-hmm.
And then find critical angle.
So the angle, okay. So maybe better is to draw the diagram. Okay. So yeah.
Yes, sir.
So this is what it is given, 12 centimeter. Okay. So you have a light. So this is the critical angle here,
Yes, sir.
and this is 90 degree. You need maybe this angle. Yeah.
Yes.
That is also the critical angle. Yeah. Because of the parallel line. Yeah.
Then find the radius.
Understood. Yeah. So Snell's law. Yeah.
Yes, sir.
Snell's law comes to look like here. So we have n1 sine theta 1 equal to n2 sine theta 2. So here n1 is water. Yeah. Or maybe you can write a sine
Find theta.
critical is equal to n2 by n1,
1.
and sine theta 2 will be 1 because it is sine 90 degree.
Yes, sir.
So this will be 1 by 1.33, which is
0.757.
okay. You are taking in radians or degree?
I'm taking in radians.
Okay, make it in degree. Let's see. In degree, what it comes? Can I calculate?
1 second, sir. I was just using the normal calculator, sir.
Understood. Sine inverse 1 by 1.33.
48 degrees. 48.7.
48.7.
Yes, sir.
Okay, take it 49. Sorry, 49 degrees. Okay.
Okay, sir.
Then how? So this you know is 49 degree. Yeah. So how then we have to do?
Sir, I stopped here, sir. I couldn't do it.
Okay, maybe take tan theta. Yeah. So tan theta is equal to
And then divided by 12 into.
r by 12. Yeah.
Okay, sir.
So tan of 49. I have to calculate r by 12. So r is equal to 12 into 10, 49. Tan 49 is
Minus 3.17.
minus 3.
Yes, sir.
Tan 49 degree.
Yes, sir.
Oh, it is minus.
Radians in radians.
Okay, okay. Take in degree.
Just a second, sir. 1.150.
Yeah. 1.15.
150.
So this will be something 13.
13.8.
13.8.
Yes, sir.
Okay. Yeah. So that's the answer. Yeah. Yeah. Okay. I think that was the last one.